This is the home page for NC Simo Solutions. At the top is the current job folder that you are working in, which contains all of the project data and machines that are available. If you click on a job, you are able to see a preview of its contents, which is useful to search for specific components without opening multiple jobs. You'll notice that NC Simo was built on Windows for Windows, as you can see the familiar tabs and icons layout that you would find in Microsoft Word or Excel, giving a much shorter learning curve as you can be up to speed in just 2 days of training. Using NC Simo, you are able to verify any program in a simple 3-step process. Step 1 is a syntax error check. Upon loading, NC Simo decodes the entire G-code from A to Z, including all subroutines. It even creates the wireframe trajectories of the toolpaths. This step is a verification or validation that catches all syntax errors, overtravels, and undefined codes. It identifies anything that would alarm out the real machine when the program is loaded for the first time. These errors are all caught up front before a simulation is even executed. Step 2 is the simulation. This step detects any errors due to motion, such as crashes, cutting the part in rapid, cutting with the spindle stopped, and cutting without coolant on. It is the equivalent of dry running the program block by block at the machine. And step 3 is dimensional analysis. We are able to compare the resultant of the rough stock cut by the G-code to the original CAD model that it was programmed from using measure, compare, and slicing plane tools to see if it falls within the specified tolerance. This is like checking the first piece off the machine and cutting open the part to measure the internal components. But before we do any of that, I want to walk you through the general layout of the work area. On the left-hand side resides what we call the job tree. It's a description of what's in the 3D window. The current project is loaded exactly as your setup would be on the shop floor. We have chosen the machine first, then on its table we have the part, fixturing, and rough stock. Next we load the tooling into the magazine of the machine. Then comes the initialization, which contains the program origins, compensations, and offsets. And lastly, we have the G-code, which is the exact language that you will be running on the real machine. Next, down at the bottom, we have the information window, which contains several tabs. The first one you see here is the Errors tab. It contains all of the alerts and alarms for the job. Up front, it displays the syntax errors, but the simulation errors will also populate here when the simulation is run. Moving to the right, we have the Status tab. It shows you all the information about the current block, including tool number, type of motion, spindle direction, if the coolant is active, if radius compensation is on, the XYZ AB position relative to the machine, and so on. The display is fully automatic and provides you with instantaneous recalculations. And then we have the Info tab, which gives you the overall values for the components of the job. It'll break the job down into sequences and give you information such as total program time, time in rapid, cutting time, length of cuts, and minimum and maximum feeds and speeds for each tool. You are able to click on a value in the table to see where in the program that peak occurred at. By adding the acceleration and deceleration times from your specific machine, we can confidently predict cycle times to within 2 to 3% accuracy. Next up is the Variables tab. If you do any looping or conditional programming, you also have the ability to track variables. You can add a specific one to the right-hand column and watch as it updates as the program progresses. And finally, we have the Graphs tab. This window will give you a graphical representation of a chosen variable. You are able to go backward and forward in the program without removing material to get an idea about the machine motion. The tool sequences are broken down by color and directly correlate to the surfaces in the rough stock. You can also see and jump between all of the locations where you've placed stops. Right now we are in feed rate by minute, but I can add another variable such as spindle speed and toggle between the two or view all of the data on the same axes. On the right-hand side we have the program window. This displays the G-code, including all macros and subroutines. Because of this, it has a significant advantage over any other simulator out there. We are able to go to the depth of the machine, including being able to decode all subroutines, tool break changes, and returns. Other programs use black boxes to mimic the real machine macros. Due to this, you can't edit or update anything. With NC Simo, when you make a macro change at the machine, you are able to copy the file and drag and drop it back into the machine folder. It will automatically recalculate for the update, and there is no need to call us to get an updated machine processed. Knowing the exact behavior of the macros and subroutines also helps us to accurately predict cycle times. The 3D window allows you to view the motion in machine or table view, or even both simultaneously. The toolpaths shown in red are rapid movements, blue is feeding, and green is cutting with compensation. You can click on any given toolpath to automatically jump to where that action occurs and to display the current block being read in the program window. If you put the tool into wireframe, you can see the compensation applied to the path. Now that you are familiar with the layout of NC-Simul, we are going to apply the 3-step process and troubleshoot this program as if we are trying to get it out to the shop floor. The first step is to take care of any syntax errors that are going to alarm out the machine. Click on the first error and it will show you which line of the program it is occurring on and how the machine is positioned at that block. The error is telling us that our z-axis is out of range by about 3 inches, meaning that we specified a retract distance in our CAM system that this particular machine cannot reach. With NC-Simul, you can use the Quick Edit button to edit the code on the fly. We are going to modify the z retract value by something slightly more than 3 inches. Hit apply and NC-Simul will rerun the error check with the new edits, and you can see that we only have 2 remaining errors. Proceed by alleviating the rest of the errors, going top to bottom, as sometimes fixing one early on can also fix a subsequent one. In the event that you want to update your CAM process, all you have to do is repost the G-code to the same file location and hit F5 to refresh NC-Simul. It will apply the new code to the current setup. There is no need to close or rebuild any components of the project. Once your window is error-free, you have completed step 1 and you know that you can load the program onto the machine without it alarming out. From here, we move to step 2, which is the actual simulation. You'll be using 3 main buttons: the reset button, the play button, and the speed of simulation slider. As I start the simulation, notice that I can zoom, pan, and rotate without any graphical recalculation, pixelization, or interruption. Use the top left-hand button to switch to table view. This locks the machine rotation in place and moves the tool around the part, which is sometimes a little easier to view. Just because we are not viewing the entire machine motion doesn't mean that NC-Simul isn't still checking for machine collisions in the background. Notice that each tool is cutting in a different color, ensuring that you can see your finishing tool during work and that your part isn't being taken to depth by your roughing operation. I can pause the simulation at any time and click on a machine's surface to show which tool was responsible for that cut and which line of code in the program it was occurring at. In the information window, we have a new list of simulation errors, and you can see the collisions in red in the 3D window as well. In the same way as the syntax errors, you can click on any of the messages to show where in the program they occur. This time when I fix my errors, I'm going to turn on brake option and put the simulation at full speed. This way, NC-Simul will stop at each error line. I can make my edit and continue on from that point. This is very useful when troubleshooting large programs if you are making edits partway through, so that you don't have to rewatch the first half of the simulation every time. If I click on the first collision, you can see that we are crashing the tool holder into the part because we don't have enough stick-out length to properly machine the pocket. What I can do is go to my tool library, where NC-Simul will have the active tool already highlighted for me. I'll then increase the stick-out length of that tool and apply my changes. NC-Simul automatically runs another syntax error check to ensure that the new tool length hasn't caused a different issue elsewhere in the job. Then I'll hit play again to continue on to the next problem in the program. This one is an example of an error that would be impossible for a CAM system to catch. If I go block by block in the program, you can see that the tool is technically out of material on both the retract and approach points, but disappears and reappears on each side of the part. However, if I hold down Control, I get to see the full decomposed 5-axis motion in between, and you can see that we're going to clip the edge of the part in 2 locations. So what I can do is use my Quick Edit tool again and edit the retract and approach values to give myself a little more clearance when swinging around the part. Now that I've reached the end of the program, I'm going to rerun my simulation one more time to make sure that I've caught and edited everything that I was supposed to, and you can see I can simulate the entire 6-minute program in about 3 seconds. At this point, you are greenlit for both syntax errors and collisions, meaning that it is safe to load and run the job on the machine. The only thing left to do is to ensure that the program is cutting the stock precisely to the specified part model. To do that, we will want to perform step 3, the dimensional analysis. There are several measurement tools to get you started with this. You are able to grab many values off the machine stock or original model, such as angles, diameters, hole-to-hole distances, or in this case, the thickness of the wall. Anything in the environment is measurable, so if you wanted to figure out what your total rotational height is going to be from the table to the top of the stock, you can grab that value as well. The next useful tool we have is the comparison tool, wherein we are directly comparing the resulting rough stock to the 3D part model. Anything that is in green falls within your specified tolerance, anything in red are areas that you've gouged, and anything in blue is excess material. You can use the slider to adjust the tolerance window, and the 3D window will update dynamically as you do so. You can see the chamfer change from yellow to green as I open up the tolerance. It can also be changed manually by inputting a step value. The final tool is the cutting plane. This is useful for viewing internal features before having to cut apart a first piece on the shop floor. For instance, if my print called out that these two drilled hole features couldn't intersect, I can drag the plane back, click on the surface, and NC Sim will show which tool and which line of code was responsible for driving it that deep. All of these features are stackable as well, so I can do a comparison while I'm in a section view and take a measurement of the amount of material that thread mill gouged. Once the dimensions for all of the features are satisfactory, you have completed the 3-step process, ensuring that your program is verified for syntax errors, collisions, and is properly toleranced. This has all been done while keeping the machines producing chips and without the risk of a crash. You can now save the modified G-code and feel confident to send an error-free program to the shop floor to be run immediately.